Is about magnetic field intensity due to straight conductor of finite length. So this infinite and finite length we are deriving for magnetic field intensity with the help of Biot law. So here we are going to discuss about finite length. So we are placing one conductor which is having the finite length from Z1 to Z2. So it is having the finite length from Z1 to Z2 and it carries a current I. And we placed it in a positive Z axis. And there is observation point P which is in a Y axis. And same we mentioned R from the distance between origin to P and uh, each even here there is an angle like alpha, alpha 1, alpha 2 because since we placed conductor in the z axis plus z axis it makes angle for the observation point. So from the point when we see the z1 the angle will be alpha 1, and from the point when we see this length z2 it makes an angle alpha 2. And here we consider a small element which is dl, small element dl. So from the point P to the small element dl it makes an angle alpha. So alpha 1 is from P to Z1, alpha 2 is from P to Z2, and alpha is from P to the small element dl. Okay, so the same thing like your infinite length, the difference is there we consider minus infinity to plus infinity as a value for z. Here it is z1 to z2 because this conductor is having a specific length. And consider a differential element dl along the z-axis at a distance z from the origin. So we can write a dl equal to dz. By placing a conductor in the z-axis, we can write dl equal to dz in the direction az. And next, the steps are same. We have our Biot law, the dh equal to I into dl cross AR12 divided by 4 pi R12 square. So first we are finding what is dl. dl is nothing but dz. And next we are finding what is AR12. AR12 is R12 divided by modulus of R12, which is same like minus ZAZ plus RAR divided by root of minus Z square plus R square. And we get what is AR12. And next we are cross producting this dl and AR12. The same like from the previous derivation. So we are writing it directly R dz A5. So now after finding dl cross AR12, we are multiplying this current I and we get IR dz A5 divided by the square root of R square plus Z square. The square root of R square plus Z square is from this unit vector. We neglected that denominator for some time being. And now we are substituting all that terms in this dh vector, which is IDL AR12 divided by 4 pi R12 square. So when we get the equation. So till this fifth equation, the infinite and finite derivations are same. So here what we are going to do is we are defining the length of z-axis means our conductor which is z1 to z2. So finite length we are substituting it here. So h vector equal to integral over z1 to z2 dh vector equal to integral z1 to z2 I r dz a5 divided by 4 pi r square plus z square the whole to the power 3 by 2. So only there is a change in the limit. For infinite conductor, the limit is minus infinity to plus infinity. Here it is Z1 to Z2. That's what. So we are defining the integral which is Z1 to Z2 and substitution method we are using where Z equal to R tan alpha. So we get Z squared as R squared tan squared alpha and dz term we have. So when you differentiate this equation on both sides, you will get dz equal to R. Differentiation of tan alpha is secant squared alpha into d alpha. Here we are using alpha because our dl element makes an angle alpha from the observation point P. So this makes an alpha angle. Previously we considered theta. Here it makes an alpha angle. So for z equal to z1, we have to change the limit, no? So for z equal to z1, z1 will be when you substitute z equal to z1, z1 will be r tan and angle will be alpha 1 to the z1. And when z equal to z2, z2 equal to r tan alpha 2. And we get what is alpha 1 and alpha 2 because we are converting z term into alpha term here. Previously z term to theta term. Here z term to alpha. So we are writing what is alpha 1 and alpha 2. Alpha 1 equal to z1 divided by r. The tan when it goes to other side it will be tan inverse. So tan inverse of z1 by r and alpha 2 equal to tan inverse of z2 by r. And now we are going to substitute all these terms in the h vector. H vector equal to our angle means z1 and z2 is converted to alpha 1 and alpha 2. Means when z equal to z1, the angle is alpha 1. When z equal to z2, the angle is alpha 2. So alpha 1 to alpha 2. And next, I r secant squared alpha d alpha a phi divided by 4 pi r square plus r square tan square alpha. So here the same, when you multiply r and r, you will get r square. So the equation comes as I r square secant square alpha d alpha in the direction a phi divided by 4 pi. When you take r squared out from the 3 by 2 power, it will be r cube. And 1 plus tan squared alpha you will get when you take r squared out. 1 plus tan squared alpha is nothing but secant squared. And when you take it out from 3 by 2, it is secant cube alpha. So secant squared and secant cube gets cancelled. R squared and R gets cancelled. So we will get the term I d alpha a phi divided by 4 pi secant alpha into 1 r is there. And 1 by secant alpha is nothing but cos alpha. And integration with respect to alpha, so rest all term will be constant, which is I divided by 4 pi r alpha 1 to alpha 2 cos alpha d alpha in the direction a phi equal to I divided by 4 pi r. Integration of cos alpha is sin alpha, upper limit minus lower limit. When we do, it is I divided by 4 pi r sin alpha 2 minus sin alpha 1. In the previous derivation, here we had a pi by 2 term. So we got 2. Here it's a general formula. So based on Z1 and Z2, it makes angle alpha 1 and alpha 2. So I divided by 4 pi r sin alpha 2 minus sin alpha 1 A phi ampere per meter. And B will be mu into H mu into I divided by 4 pi r sin alpha 2 minus sin alpha 1 in the direction of pi Weber per meter square. And this is H and B for finite length conductor which is placed along the z-axis. And here we have a sign convention for alpha 1 and alpha 2. Means in the derivation we placed the conductor in the z-axis plus z-axis. So the finite length has three conventions, three sign convention. One is placing the conductor in the positive z-axis where z1 and z2 both are in positive z-axis and it makes an alpha 1 and alpha 2 angle. Then alpha 1 and alpha 2 both will be positive. Means alpha 1 and alpha 2 angle comes above the observation uh, angle observation point. Means from origin to P, it makes a right angle, right? So this is a right angle. So for this right angle, both the length of the conductor comes up to the observation point. So alpha and alpha 2 is positive. And see this diagram where this is a right angle means the distance from the point P to the origin. And when we see the conductor, both are placed below the observation point. Means alpha and alpha 2 both comes in negative. Both we have to consider negative. And next, when we place a conductor like this, where the observation point is a midway, observation point and this perpendicular direction, it is in the midway where z1 is below and z2 is above. So here what happens, alpha 1 will be negative and alpha 2 will be positive. So overall, when the length means when the conductor comes above the perpendicular distance, then it is positive. When it comes below the perpendicular distance, then it is a negative. So there are three conventions, alpha 1, alpha 2 positive, alpha 1, alpha 2 negative, and alpha 1 negative, alpha 2 positive.